Stephan Ohr.
Good morning, everyone. I'm grateful to Dongbu HiTek for sponsoring this conference. This is the fifth year in a row for the Analog Leadership Forum, and I'm grateful for the opportunity to speak to you this morning. My conversation will be a little bit different from Tim's. Tim's went down to the device level, actually looked inside, saying, okay, what are some of the transfer functions? Mine will be on a different level. I'll be more the 30,000-foot level, trying to assess, okay, what are the markets that are going to grow? What are the forces that make them grow? What Tim and I do share, and many of us in this room, is we love analog. We're very devoted to the technology and the products, and we'd certainly like to see it grow. Which leads me to the opening slide here. I call it the 101 lecture. So many of my companions look at digital CMOS. They watch the progression from 90 nanometers to very deep sub-micron layer levels, 45 nanometers, 28 nanometers. Products are going out there with 22 nanometers. And they're enamored with Moore's Law and firmly convinced that this is going to be like a whirlpool that absorbs everything. Analog, power, it's all going to go to 22 nanometers. I have to say, stop. That's not what's really going to happen. For one thing is, we know that the digital transistors and the analog transistors behave differently. Tim pointed to some of the problems with digital CMOS in his presentation. What you want the transistor to do if you're recording digital signals is you want them to switch on, you want them to switch off. You want it to do it fast, and you want it to do it recognizable. It doesn't matter how sloppy the transistor is, how much it leaks, how much it makes noise, how much it clatters when it goes up and down. All you want it to do is go up and down, be able to read those states. And the irony of Moore's Law CMOS technology is that the more you shrink your feature size, the easier it is to force these things up and down. So in fact, you can imagine, don't have to imagine, you could just look at the Intel processors, the Xeon processors that are going into servers, literally billions of transistors per chip. An analog guy looks at this and says, okay, what do you do with a billion transistors? And the answer might be you start fires. You do have this issue of power consumption. Intel struggles with it. Guess what? They turn to the analog folks for solutions. With analog, for the most part, your transistors are behaving differently. You want to control their on and off states. In some cases, you want to suspend them, bias them in such a way that they hang up between on states and off states. If you're building an amplifier, in fact, you want that linear transfer function. You want a smooth analog between your input and your output signal. You have to build bias circuits. You have to worry about noise levels. Even when you're doing something like a controller with a lot of digital logic, you want to watch out for your noise. You want to make sure your states are under control. This does not scale. It certainly does not scale easily. If you design a circuit for a particular geometry, 0.18, 0.13, if you want to bring it to a lower geometry, you may in fact have to redesign the circuit. One level that saves you some investment in process technology, but it does present engineering problems. The thing about analog and digital as they work together, they're not mutually exclusive. That as the digital CMOS business grows, we're doing more video processing, we're doing more digital signal processing. Turns out the analog interfaces grow along with it. So in this talk, I'll give you an idea. Okay, how big is the market? What are the forces driving it? I'm focusing mostly in this talk on standard analog components. These are multi-market building blocks. They tend to be very inexpensive. They tend to be very versatile. They're very widely used. If I show you some revenue growth on it, a lot of it is unit growth with predictable, ideally controllable price declines, but nonetheless high unit volume, relatively stable ASPs, although they're on a downward slope. I'm not going to say too much about application-specific parts, with one exception. I do have a slide in here on the power management ICs that are used for mobile handsets. That's a bit of a technology challenge, but it's also a growth area that many people say, okay, we'll develop some revenue growth around it. As we talk about the requirements, I'm going to spend a lot of time talking about power management issues and power management devices, including power transistors. As we go down the slope, then the questions for manufacturers, both ODMs and foundry service vendors. If we're doing power management, what are some of the special characteristics that we need to worry about? And at the end, I'll actually, keep the I wouldn't call it bad news, but sobering news toward the end, where we look at, okay, what's the semiconductor industry as a whole going to do in the next couple of years? Okay. This is the standard analog parts market. $20 billion in 2011, based on our market share compilation, where we looked backward at a previous year's revenues and said, okay, what was going on out there? There are 5 parts of the market. This include data converters, amplifiers, voltage regulators, interface ICs, and there's a category called other, which is really timing controllers. And this one is, growth on this is a little flat right now, but we actually do expect it to grow as some of the silicon clock vendors tap into the market now dominated by quartz crystal oscillators. Notice there your voltage regulators, more than half the market. On this particular slide gives you an idea of some of the growth associated with these parts. I'll comment on them. I should actually take a moment. I want to just talk to you a little bit about application-specific analog, give you a context for this. The standard analog parts business is, as I say, $20 billion in 2011. This year, it'll be a little less. It'll be down a couple of percent. It hasn't been a great year for a lot of manufacturers. This represents essentially 40% of the total analog IC market. The other 60%, some 36, 38 billion, is an application-specific analog. The part, not as quick to flash a foil at you because it's hard to categorize those particular parts. You have to go through them application by application. What is a PCI Express interface? What is a disk drive read channel? What is an inkjet thermal control nozzle? These are essentially mixed signal parts, and it's a judgment call how much of it you'd say is analog, where you would put them on a particular spectrum. If any of you are, in fact, interested in working with me, Gartner, on the dimensions of the application-specific market, I do have estimates, and some of the things that I'll show you in this presentation rely on those. Sorry. Standard parts. This curve is a little flatter. It goes up and to the right, as we would expect to show some growth, but it's flatter recently than it has been in years past. Overall, the standard analog parts market would track the semiconductor industry as a whole. If the industry grew 5%, analog might grow 5% or 5.5% or 4.8%. It's generally on the same curve. Some years it grows faster, especially as a lot of these parts might be considered commodities, so in which case you take a chance, you build inventory, you stockpile them. The order rates might show up a little bit higher than demand. Other years, right now, the CAGR here is something like a 4.6 for this standard analog for the semiconductor industry as a whole. I'll show you later on. We're showing 4.9. So right now we're lagging the semiconductor industry, but basically on the same general slope. Let me spend a couple of minutes talking about the part types in here and the forces. When you look at amplifiers, what you're generally working on is low power consumption, speed, or precision. Those are the things that will dominate amplifiers. They are sold by the truckloads, but when you get into data converters, something different is happening. Despite the setback in equipment construction, the data converter market does seem to be slowing. And what I attribute that to is essentially a stratification of the market and a fracturing on the low end of that. The things that will do revenues among data converters are very high-end, difficult to make parts. These would include the A to D converters that go into cellular base stations. These parts will sample at 150, 200 megahertz if you can do it, 250 megahertz. For base station receivers, you want a very high resolution to make sure that you're capturing all your low-level signals. So these are 14-bit parts or 16-bit parts. The deployment of those actually matches the deployment of cellular base stations. Heard news this morning that not only is base station deployments a little sluggish going into the future, but I'm hearing about U.S. congressional rulings that may impact how many overseas suppliers would be able to touch these parts. So that essentially would slow down the market. For interface circuits, think of all the places you would put a USB interface, and it does seem to multiply. You put them in cars, you put them in clock radios, you put them in your stereo sets, you put them in your home TV. At the same time, your pricing goes down rapidly. And you also have a factor where in the portable devices, the USB interface is actually married to the power distribution and battery charging system. So in fact, here's a big place where you've got a USB interface, but the numbers and revenue that you count there is small. Once again, with the other analog, your interest there is in essentially timing controllers, clock generators, repeaters, delay lines, and it's right now you have some of the market being pulled apart by Intel's election to include the timing controllers on their Intel CPUs, so that in fact wipes out a good chunk of the market. But at the same time, you see more of the precision devices showing up in communication circuits and things like digital consumer electronics. So you've got some growth in, there. Right now, it's a little sluggish. That market is expected to grow a little faster in years to come. The big thing, and most of the slides I'll show you, around this issue of power management. This is the answer to the question, why should I care? This is the curve that goes up and to the right. Initially, when you think back to the beginning of the century, if I could use that expression, in terms of the revenues, it looked like data converters, amplifiers, voltage regulators, they were all the same general vicinity, but the growth in the voltage regulators has been much faster. And this is, it is mostly, for this curve, a unit growth. The more complex you make your system, and there are new systems being iterated all the time, but the more complex your system, the more power management devices you need. And on some levels, it may serve no purpose whatsoever except to buffer one section of your circuit or your system from another section, just to have some buffering, make sure the power requirements of one part of the system doesn't drag down the voltage level in the rest of the system. Nonetheless, the complexity will drive the unit growth, and this has been a pretty historically, if you look at over this period, a pretty steep curve. This is the near term, or certainly within the next 5 years. We got to 2016 in our projection for the voltage regulator market by industries. At one point, when I had a steeper curve, it was easier to distinguish parts on here that, or markets that would in fact grow faster than others. What you do see, it's big and fat in terms of revenues, expected to reach $3.6 billion in 2016. On this chart, it does show the fastest compound annual growth rate. These are the parts that go into the computing environment. And I'll detail in a minute what happens in the computing environment to drive some of this. But this seems to be a big driver here. Next to that is the industrial medical realm. Lots of systems, electric trains are in here. Traffic systems are in here, as well as medical devices, scanning equipment with very, very high voltage interfaces. That turns out to be a driver for voltage regulator growth. You've got at least positive CAGRs for the rest of the markets. But let me, in this slide, spend a little bit more time on the computing environment. One of the things, or the big thing that is a concern is energy transfer efficiency. Didn't want to show you 60 slides today, so I did a bit of pruning, but one of my favorites had been the layout of a server card showing the CPU, the memory system, the high-speed I/O, which tends to be FPGAs, your Intel server processor. On that particular historical chart, 2005, consumes 140 amperes. Well, guess what? The Romley part type that's going into servers, the latest incarnation of what Intel calls the Ivy Bridge, that thing wants 200 amperes, and I'm looking at data associated with the 2013 introduction of the thing Intel calls Haswell, and the voltage regulators are calling out 400 amperes. So the big question is, okay, how do you feed these machines, control their voltage? In between them, your DDR memory banks can consume, yes, Samsung has got low power DDR memory, but today's standards, or at least what's out there in terms of legacy equipment, 80 amperes to power your memory bank. Your FPGAs, which do the input-output address generation decoding function, those things want 25 amperes apiece. So the question is, how do you power them? And the simple answer is a type of voltage regulator we refer to as a DC to DC converter. Some of you may think of them, okay, it's a POL, point of load converter. Sometimes we use the terms synonymously. Somebody says they're getting into the POL market. They're really thinking about DC to DC converters. These essentially are switch mode parts pulse generators, whose pulses are summed to make a particular voltage level. They are used in conjunction with power transistors. The thought about the use of those parts versus something like a three-terminal linear regulator is, your three-terminal linear regulator works like a valve. You could turn it up, turn it down, so you almost have it's an error amp that controls the current going through a series pass transistor. That thing is always cooking. So 30% is a very good efficiency number to get from a linear regulator, but it generates a lot of heat. The DC to DC converters, especially when they're coupled to a fast switching, efficient pair of power MOSFETs, have much higher energy transfer efficiency, and the issue for this machinery is heat generation. As an aside, there are political arguments. Who pays the bill? The data center manager paying an electricity bill is one cost. The equipment is a totally different cost. And if I say, okay, pay a higher price to have a more efficient part, sometimes the equipment manager might give you an argument saying that's going to increase my equipment costs. And you can't say, well, the data center manager will be happy because it's not, the equipment is not his budget. Nonetheless, the trend is toward, okay, more efficient parts. So what happens is, you see this market. And here's a place. It still shows double-digit CAGR, compound annual growth rate. This is that voltage regulator segment broken down by part types. And what I've been doing for the past few years is breaking the voltage regulator content down by high current linear, low voltage LDOs, switch mode, portable switch mode, power controllers, the DC to DC converters, and I take in this count I'm actually taking a module that might include separate transistors plus the pulse width modulator, actually including that as a DC to DC converter. You've got AC to DC converters. We have numbers for multi-phase controllers, sequencers, so you've got hot swap controllers lumped in there, and the battery charge controllers. This includes things like your lithium-ion safety circuits. It includes your fuel gauges, and then I still have some revenue with Tim's parts, the standalone references. On this particular chart, got the most growth associated with the DC to DC converters. Your driver is cloud computing, your big data center machines that say, okay, I need to minimize the heat generated, and the way to do that is to use a more efficient part. You've got a decent growth rate associated with AC to DC converters. Frankly, I do have some apples and watermelons mixed in here. The apples, not the company name, but the small things, battery charge controllers. You've seen them. Amazon is distributing with their Kindles. Black Rim is distributing them with their Blackberries. These are very small plug-sized devices that have primary side AC to DC converters in them. The market also includes things that would go into LED light bulbs, things that would convert AC to DC to power your LED incandescent bulb replacement. Those have to be very inexpensive parts. Right now my lumping, my system of categorize actually includes the AC to DC converters that will support UPS, the uninterruptible power supply systems, and you can imagine the pricing on that is much higher. This, though, gives you a general idea of the revenue growth. Manufacturers, okay, people have to think about wafers. If you could translate this number into how many die into how many wafers. this particular chart might be helpful. As I said about standard analog right from the beginning, the market generally shows high unit growth. The parts are very versatile, and sometimes systems manufacturers will stockpile them. You generally have decent unit growth. You have to worry about ASP decline. If you want to take a look at the high current linear parts, flip back for a second, pricing decline. And this has to do with multiple sources of supply. We're talking about a 1 ampere 3-terminal regulator that goes for about 11 cents. It's difficult to make money in this area, and the revenue growth is negative. If you look at the unit growth, however, it's positive. It's not an exciting number, but in fact, it is there, and some manufacturers will continue to support the 3-terminal regulator business simply because that gives them a foot in the door on the higher ASP parts. All right, we compile market share. Unfortunately, the level of granularity is, I can only guess at what it might be for the DC to DC converters, the AC to DC converters. In each case, I can name some of the prominent names and pay attention to their product introductions. This is big picture for voltage regulators in general. TI has led this market. It actually used to be a contest with National Semiconductor. Somewhere around 2008, TI took the lead in power management ICs, kept going. National had some internal problems of their own, which actually allowed Maxim in the intervening years to take number 2 slot. But National's power management revenues were so significant that if you take, if you take a half a year's of 2011 revenues, give them to Texas Instruments by Gartner's accounting rules, where they really took possession at the end of the third quarter. By our accounting rules, we have to give them the whole quarter. So it's 2 quarters of national revenue number in this Texas Instruments figure, and a half years of National's power management IC revenues are still strong enough to give them a slot in the top 10 for 2011. These are familiar names to you in the power business. Power Integrations has been on our top 10 power management list for a few years now, as with the Taiwanese company Richtech. This is something I alluded to. Didn't post the revenues, but I can tell you what they are for handset, mobile handset, analog content in mobile handsets. And this includes things like media processors, audio codecs, power amplifier PA parts, transceivers. If you count up all the analog parts, and the counting would be application by application or top down, you get roughly about $9 billion of application-specific analog ICs going to the mobile handset business. That's out of $27 billion total, so it's a fairly significant proportion. On your power management ICs, depends on how you count them. These are complicated parts that have 2, 3 switch mode regulators attached to them. Rated 300 milliamps, so they actually don't be rated 1.2 amps, just in case you have to worry about a spike. but generally you want them to give you 300 milliamps for your apps processor, 300 milliamps for your baseband processor. There might be more than one. It might have I call it a media processor. I've been increasingly writing about audio hub devices, but you might need another 300 milliamps for that. But then you have anywhere from a dozen to 22 to 26 LDOs. You have a DC to DC converter that might be a boost converter that backlights an LED string for your panel interface, or the older flip phones or soap bar phones that have keypads. You have LED backlights for that. It includes the USB interface and access, if it's not on the chip, the lithium-ion battery charge controller. Nonetheless, you're talking to that through this particular device. There is ongoing, how much could you include on this particular device? People have argued and lobbied and built parts that have stereo audio codecs. There's a lot of manufacturers who throw up their hands and say, I can put a stereo audio codec on there, but it's going to be very, next to a couple of switch mode parts, it's going to be very noisy. There is, I've written a disintegration of the audio function. Increasingly, the codec remains a separate part, especially as you start anticipating your mobile handset's going to be used as a media control center at home. So you want to be able to transfer your audio with full fidelity to your home theater hi-fi system. So there will be an audio hub on that device, which could use another 300 milliamps by itself. You keep the stereo audio codec separate. Market for this type of part. Smartphones is on something like a 30% a year CAGR. If you just take the smartphone growth portion of the power management IC business, you include the PMICs that go into tablets, such as the Apple iPad, you get about 1.9, almost $2 billion of revenue. If you step backward and say, wait a minute, I know there's a lot of low-cost Nokia phones still out there, basic phones, things built around the older CEVA chipset that Infineon was using, or TI's own La Costa. You find another $1 billion in revenues there. They mentioned in this context, the complex part, if you're going to build it, it requires some talent, because invariably you've got a fairly dense CMOS geometry. A lot of the parts out there are still 0.25 micron. Increasingly, you're seeing 0.18, and there's a couple of manufacturers out there that have promoted 0.13 geometries to build this, and then some kind of interface to your power sources. So thinking about something like a bi-CMOS part in a 0.18 micron geometry, which, in a moment I'll talk about some of the process variables, but from my conversation on DC to DC converters, I did want to say there's a pointer to power transistors, MOSFETs, IGBTs, and other devices with power technology. The thing to look at here is, once again, as with the DC to DC converters, the power transistors, the thing with the highest compound annual growth rate, are in the computing sector. Industrial, once again, is following close behind in its use. Consumer, as you would expect, is a bit flat. Cost issues there. And also, I want you to say you're using a different type of device with a different ASP in a lot of the consumer products. What I've done is, this is the power transistor market oriented around transistor part types. The three big ones are the MOSFETs, the IGBTs, and this part that remains inside of consumer devices, your bipolar power transistors. In terms of figuring out, okay, how are these devices different? Why is it so easy to sort them by applications? Is the bipolar devices can conduct current in more than one direction. You could also bias them so that they could behave that amplifier function, and as a consequence, you still see them in audio power amplifiers. You also see them in motor drive circuits, where also you use what is called the long tail as resistance against inductive kickback from your motor coils. Unit-wise, the MOSFETs, once again, it's being driven by the same technology that drives the DC to DC converters. It's switching, these are switching devices essentially attached to your pulse generators. High side parts are connected to your positive supply rail. Your low side parts are connected to ground. A talented manufacturer of these parts will make an effort to distinguish how does a high side driver have to behave different from a low side driver. But nonetheless, these totem poles are widely used with the DC to DC converters, and will show us some market growth. Your IGBTs, they have some of the switching, the response to gate drive, similar to a MOSFET, but some of the long tail of a bipolar, a lot of useful in motor drive circuits, increasingly used even as switching devices in high voltage circuits that would be offline switching power supplies, especially something that has to interface with a 220 volt AC line. You also see they're widely used automotive circuits for your window lifts, your side view mirror drives, your what used to be called the moon roofs on your cars, all those things, motors powered by IGBTs. As I did with the power DC to DC converters, we do market share, who's leading in power transistors. This area had been, I don't know, I think complacent is not quite the best word, but hesitant to invest in new manufacturing capability, even IR, rather than put up new plants, farmed out some of their manufacturing technology to a foundry service provider. Infineon changed things. What they did is they put up a 100,000 square foot facility in Malaysia dedicated to MOS device making, and essentially did in the power transistor market what TI may about to do in the DC to DC converter market. They had extra manufacturing capability, which allowed them to increase production, keep their costs down, and undersell. They weren't as aggressive as they could have been, but I have heard they've done competitive pricing, and they do show up here as capturing market share. In terms of the names, they've displaced Toshiba, which was once well known in that part, but Toshiba's problems, as with a lot of the Japanese manufacturers, stuck by the high cost of the yen. What I did is to see if I can get a little bit more granularity on the power transistor market. I did a bit of a bottoms-up count. I actually asked by application, what are the devices being used How many of the devices are there per system? How many systems do we think will go out there? This is not the entire power transistor market, just selected devices, but it ratifies some of the thoughts that I was suggesting. When you look at unit growth, it's the low voltage MOSFET, the 30 volt MOSFET part. That was the one that would support DC to DC converters in computers' power supplies, especially where you're operating at 5 volts or less. Your bipolar parts still have some, and this is unit counts, by the way, millions of units. You still see the bipolar parts in audio amplifier circuits. The IGBTs are used in automotive applications, but I've actually seen a 400 volt part used as ignition triggers. Lighting ballast seems to be a growth opportunity, but your parts, especially if you're coming off of an industrial building where you're not getting the 220 volt AC residential feed, you're actually getting the industrial transformer feed at 480 volts AC. So if you're going to interface with that, then you need a safe operating area of up to 1,000 volts or more. Once again, here's the AC to DC converters that go into UPS systems, your AC motor drives. This is more residential, but your washing machines will use banks of IGBTs rated 600 volts. And if indeed you want to talk to the power line, that 480 volt AC interface, you need 1,000 volt, 1,200, or there are in fact some 1,700 volt parts out there. What this means is you can start graphing out your power transistors according to things like switching speed, your F sub T's, and your voltage requirements. There is, on some levels, this curve is predictable. The higher the power you're pushing through your power transistor, the more sluggish it's likely to be. But an issue, if you're talking about alternate energy inverters, trying to get those on the power grid, at this switching speed, your parts are going to be, you're going to have big transformers, you're going to have big capacitors. If in fact you could raise the switching speed, if you can get it into the 100 kilohertz range as opposed to 10 kilohertz, then in fact you have the opportunity to reduce the size of your capacitors. You can reduce the size of your inductors. You can actually make the energy transfer a bit more efficient. A lot of manufacturers, especially those operating above 600 volts, have an interest in saying, okay, can I move this curve to the right? That actually sets us up for things like gallium nitride and silicon carbide, whose promise is higher transition, faster switching speeds. The good news was on the other slide. It's not exactly bad news, but it will be a while before we have a good volume of devices out there. Right now, with the gallium nitride devices, there's a lot of excitement because a company like International Rectifier says, okay, we could integrate DC to DC converters with power transistors, make a single chip device that will have higher switching speeds than a lot of your DC to DC converter modules. We can do what the computer guys say they want from us. We can make a smaller part, higher power, faster energy transfer, higher energy transfer efficiency, and smaller form factor. The problem is that there's still experiments going on. That for one thing, the gallium nitride devices, your straight transistors, are depletion mode devices. They're easy to turn on, but then they stay on. You have to create a negative rail, do something with them to force them to turn off. At APEC, TI introduced it's a silicon power FET device, but it's essentially intended as a gate driver for the gallium nitride transistors. Tells us two things. One is we still need an infrastructure. Do engineers know how to use a depletion mode device? And the answer is not really. You have to teach them, or you have to cascode the gallium nitride device with another type of driver, so it actually functions as an enhancement mode device. But there's a little work there. If you go around, I visited the APEC conference, Advanced Power Electronics Conference, in February, and talked to a lot of manufacturers. And they said, okay, if you use FET drivers, you're in fact slowing down the gallium nitride switching speed, in which case do you lose the advantage over silicon. There are others more cynical, that there were a lot of manufacturers who looked at the efforts in gallium nitride and called them high school science fair projects. And what they were thinking about, if you go onto the websites of some of the leading manufacturers or the leading advocates of gallium nitride, you see a lot of conference papers, but you don't see data sheets, you don't see samples that you can buy. Transform told me at the conference they had a JEDEC qualified 1200 volt transistor at the conference in February. I spent a lot of time looking at their website trying to find that transistor. Yes, it does show up. It showed, it was finally introduced. Here's a part you can buy. Here's the specs, September 12th, just last month. So there's a gap between what people say they can do and what they actually will do. For that reason, I project that gallium nitride use is going to be pretty small for a while. Maybe by 2016, we'll see something as we would with LED lighting, that suddenly there's an infrastructure, suddenly there's multiple sources, and you have a takeoff point. With the silicon carbide transistors, you in fact, there's an infrastructure starting to build. There are devices out there. There are devices that you can go to a distributor and buy. You can go to DigiKey or Avnet and buy these parts. Not cheap. Your silicon transistor might be $1.60. Your silicon carbide transistor is an order of magnitude higher, $16, $20. But you can buy them. You can experiment them. You can decide, all right, if I need high-speed switching at high voltage, what are the applications? You can start to do that. For that reason, so you use one battery, right? No, it was, I just wanted the pointer. Yeah. No, this pointer seemed to have, okay, it's come back to life. Either that or I was pressing the wrong button. I see life, or the silicon carbide, that'll come on the market a bit more quicker than the gallium nitride. I'm starting now to hear promotions for the Electronica show, which will be in Europe next month. And some of the manufacturers are saying, we have silicon carbide products to show you, come see us. So in fact, we're a bit further ahead with silicon carbide than we are with gallium nitride. Okay. Now, if you buy my argument, it's power management is our chief concern. That's where we're going to place our bets. That's where we're going to make our money. There's some things the ODMs, the manufacturers like TI, foundry service suppliers like Dongbu and Dongbu competitors need to think about. One is this shift toward the tighter CMOS geometries. It used to be that 0.25 micron, 0.35 micron was the sweet spot. There was a lot of work still being done at 0.35 micron, but because of this need for higher logic density, even on something like a power management controller part, you see the shift toward the 0.18. As I said, there are some 0.13 designs out there. If you look at things like ISSCC conference papers, invariably nobody's doing a data converter at 0.35. All the new designs are 0.18, 0.13, and immediately what you read is the designer is actually thinking about integration with some other part of that geometry. For power, the new emphasis on BCD. I think Dongbu calls this a BCD MOS. We should really develop a nomenclature because a lot of the early pioneers of BCD, including TI, ST Microelectronics, would refer to BCD. But if you, for example, do a Google search for BCD, you don't find bipolar, CMOS, DMOS. You find binary coded digital. So we really have to work on the nomenclature. But one of the things is, okay, we have to get really good at packing power transistors onto the same substrate with CMOS logic. That this issue that the server card manufacturers are thinking about. I want higher current, less heat generation, smaller packaging. You can get that with a mixed technology process. There are different opinions. Okay, what's state of the art, and where can we go with this? My own feeling is that for BCD, for integrating the power transistors, 10 amperes is about state of the art. With higher currents, then in fact we have to think about outboard transistors. In many cases packaging the transistors in the same IC package as your voltage regulator. There's a thought, okay, if you can do the higher current in a BCD process, you are going to have customers for it. But there's a lot of cleverness that needs to be mastered there. The way transistor makers, especially the MOSFET transistor makers, have gotten more current out of MOSFET devices, they parallelize meaning to put them in parallel. They parallel multiple MOSFET cells. The way it works is, in general, you can lower the on resistance of your MOSFET by paralleling these cells. You can also increase the current carrying capability. But what happens is by spreading the cells, you're actually increasing the die size, and you worry that you might wind up with a monster-sized chip. On this chart, I showed the TI NextFET structure, but Tim informed me that this may not necessarily apply to the BCD process they use or the one that you use. The thing that I was drawn to is the planar conduction path. That I guess the simple message would be, can we increase the current carrying capability, keep reasonable RDS on without making a monster-sized chip? That would be the technical challenge. And the other thing associated with this is we now believe that RDS on works against switching speed. That as you decrease RDS on, then you start increasing your gate capacitance. You make the devices harder to turn on, turn off, and that slows them down somewhat. You need high voltage processes. For offline switching, 700 volt, 600 volt minimum safe for interfacing with that 220 volt AC line. And there's something that analog, all the companies worry about when they look over their shoulder at what TI has done, is the 300 millimeter wafer usage. Here's in trying to say, okay, here's what we need. What is a company like Dongbu doing? Certainly moving in the right direction. There's a BCD process that you have with the 0.18 micron, 30 volt lateral DMOS power FETs. And I'm not sure what the exact number is. In a previous year, I would have been able to say it off the top of my head, but I believe you're doing fairly low RDS on. These are the parts that would support your offline AC to DC, LED lighting, your 600 volt power appliance controls. The TI example, everybody has to sit up and take notice of this. I went to a demonstration of the RFAB facility in Richardson, and was very impressed, but it made me calculate, okay, what is the capacity? We figured out that TI could service single-handedly service 10% of the DC converter market in the next few years, and that would be very severe on their competitors. But with all the capacity that they have, there's a risk. If demand continues to slow, then you have excess capacity. TI put Richardson together with pennies on the dollar from equipment from Kumunda, so it's not like they have to do 100% utilization. On the other hand, there's still some debt from the national acquisition, so we're all hoping for good market conditions. Which brings us to the last part of the presentation, and I have to go quickly. Demand is slowing. We're seeing in PCs, Intersil just announced their earnings. They took a terrible hit from a slowing in the PC market. We still have some inventory overhang that we have to burn up before we're actually recording new orders. ASPs are weakening. And we still got this issue of Europe, uncertainty. And all of this is depressing the economic outlook. We had initially seen 2013 as a growth year, and we will see some recovery that year, but the recovery we'll see in 2013 is actually what we expected in 2012. This repeats what I've just mentioned about uncertainty in Europe. This is a worldwide condition. People are hesitant to buy. Your inventory overhang, you're slowing the PC forecast, even your mobile phone forecast. It's got some growth, but it is slowing. Let me jump to the actual numbers. And this shows the difference between our second and third quarter forecast. We're actually lowering expectations going out. We see 2012, it'll be positive for the semi-industry as a whole, but barely, and analog will come down a couple of percent. Your contributors to growth, once again, smartphones, media tablets, PCs, not as much, servers, automotive, and LCD TVs account for enormous parts of the semiconductor growth. Here's your Semiconductor Initiative forecast by part type. Analog is on a slow growth curve. I'd said 4.6. Actually, it's showing, doing it from memory, but it's actually showing 3.6. The semi-industry is 4.9. We're hoping for better times, but this is what we're predicting based on what we now know. Last thing to mention is the ecosystem. We're calling it the Sigma. This includes Samsung, Intel, Google, Microsoft, and the A might be a double A for Apple and Amazon. But one advice to semiconductor and equipment manufacturers is that to try to move in the orbit of these companies, because increasingly they get to pick and choose and can mean success or failure in particular markets. On that, I'd say we all hope for, didn't necessarily promise you good news with the semiconductor forecast, but there is hope for analog. And if you're looking for some of the niche markets or places where there's light, I can certainly talk to you. I welcome your questions. Meantime, thank you very much.
네, 스티븐 오 씨의 강연이 마쳤습니다. 혹시 질문 있으신 분들은 손을 들고 질문해 주시기 바랍니다.
Cost advantage, COM side cost advantage of TI.
On the 300 millimeter wafers, we had published a rough calculation to the effect that they have a 30% cost advantage with the 300 millimeter wafers. Now, on the other hand, when you look at what's the cost of finished goods for an IC, you've got almost 70% in packaging and testing a lot of the back-end parts. The TI will have a market advantage, no question about it. In that particular slide set, and there's a document that Gartner just published with my estimate, we believe that the TI could get something like on a 300 millimeter wafer, power management IC, they can get 2,907 good die off of a 300 millimeter wafer. A similar yield on a 8-inch wafer would give you something like 1,228 die. So the ability to produce more good die for wafer in one manufacturing operation gives them an enormous cost advantage. But